Let's take a look at Lesson 24, Solutions to Systems of Linear Inequalities in Two Variables. This is on page 351 in your student workbook for Illustrative Mathematics Algebra 1. Go ahead and highlight our objective today. Let's look at situations where two constraints that can be expressed by inequalities must be met simultaneously. A silly riddle. Here is a riddle. I'm thinking of two numbers that add up to 5.678. And the difference between them is 9.876. What are the two numbers? So first of all, just exploring this in class, obviously any pair of numbers that does one or the other may not work for both, right? But so let's just test some out. For example, a student said 3 plus 2.678. And then obviously that adds up to this 5.678 if you test that on a calculator. And then any pair of numbers whose difference is 9.876. So to stay in positive numbers, I had students choose a larger positive number. And then in order to figure out what would result in 9.876, you had to grab a calculator and do 12 minus 9.876. And that would give us the difference that we're looking for to subtract right here, 2.124, for example. Now, what are we really doing here with these in order to add up to 5.678 and to subtract to 9.876? We're taking any two numbers like x plus y, and those two numbers add up to 5.678. And then we're taking those any two numbers whose difference is this. Solve the riddle or solve the system. So we notice that these these y's cross out, and then we get two x's, but this is going to be something we have to add up for sure on a calculator. Look at those numbers. So pause and grab your calculator. I'm getting 15.554. How'd you do? And then we divide that by 2. We get 7.777. And then we have to plug that back in to get the y. So grab a calculator, subtract 5.678 minus 7.777. I'm getting a negative 2.099. So the solution to this system, my two numbers that add to make 5.678 and subtract to make 9.876 are 7.777, comma, negative 2.099. There, how'd you do? There's our riddle. To make a quilter is buying fabric in two colors, light and dark. He needs at least 9.5 yards of fabric total, and the light color costs $9 a yard, the dark color costs $13 a yard, and the quilter can spend up to $110. Here are two graphs that represent the two situations, and we're using X to represent yards of light and Y to represent yards of dark. So writing the first inequality, 9.5 yards in total, we can see right here that there's this point around 9.5 here and 9.5 here. So the total of the two fabrics has to be at least 9.5. So this first graph A represents that inequality. And then the second one, 9 per light fabric, 13 per darker fabric, has to stay under a budget of 110. Okay, and this one goes with the second one. If I actually tried getting the intercepts, I would see that it comes out just after 12 and just over 8 when I divide by 13 into 110 and divide by 9 into 110. Okay, so I've got my two inequalities. Oh, write them here. The length constraint is the first one. And it says select all the pairs that satisfy this length constraint. So we're just adding them. Is 5 plus 5 greater than or equal to 9.5? Yes. Is 2.5 and 4.5 greater than or equal to 9.5? No, not enough fabric. Is 7.5 and 3.5 greater than or equal? Well, that equals 11, so yes. Is 12 and 10? 12 plus 10 is 22, so that's a yes. So the correct solutions to this are here, here, and here, and the no was that one. Next, write the other inequality. Are all these pairs satisfying the constraint? Now, for this one, if I look up here at the picture, 1, 1, definitely in the shaded region. 4, 5, definitely in the shaded region. 8, 3, right on the line, solid line of the shaded region. And 10, 1 in the shaded region. So we can do the algebra, or we can just go look at the shaded region to see if it fits under our constraint. Why does 2, 2 satisfy the cost but not the length? 2, 2 would definitely be under budget. But it's just not quite enough fabric in order to make my quilt. Unless you were making a baby blanket or something, right? It's way too little fabric. Find at least one pair of numbers that satisfies both constraints. Be prepared to explain how you know. So if I took this one, 12.1, and just over 8, and I connected it, so it's like I'm combining both graphs together, and then I'm shading under for this one to stay under budget. I'm looking at where the yellow touches the blue. And so we're looking at this region right here. And down here it says one pair of numbers that satisfies both. Give us something in that pink region. And so we could say 9, 1, for example. Or I'm sorry, 10, 1. Would be within that region. What does the pair of numbers represent in this situation? So if you go back up and look at that constraint, remember the bottom is the light fabric and the side is the dark. 10 yards of light fabric and 1 yard of dark fabric. Okay. Now in this next one, there was 3 scenarios given. I'm just going to do one today, but you could probably ask your teacher for the solution of the other 2 if you were interested. Let's just do the concert tickets. We're trying to write 2 inequalities in order to put those 2 inequalities into a system of inequalities on the graph. So we've got a constraint based on how many seats can be sold. Lawn tickets and seat tickets, fewer than 400 in total, were sold. And I'm going to call X the lawn tickets, Y the seat tickets, and fewer than 400 were sold. And then the lawn tickets are $30 each. And 50 for seat tickets. We need to make at least 14,000. So to get the X and Y intercepts of the first one, it's just going to be 400 and 400 since there's nothing to divide. And then 30X for the X intercept, the Y is 0. You just need to divide that by 30. And for the Y intercept, the X is 0. We need to divide that by 50. All right, let me grab my calculator. 14,000 divided by 30. I'm getting around 467. We have to round that one. And then over here, 14,000 divided by 50 is 280. No rounding necessary. So what do we want to count by down here in order to fit these on the graph? Well, we need to get out to 400 or 467. So what if we count each line by 50? And so that would go 50, 100. Notice I'm only writing the hundreds. And what are we going to put on each of these axes? Down here is going to be the number of lawn seats. And on the side, it's going to be, lawn tickets. And on the side is seat tickets. So let's go graph by intercepts here. For the first one, we're going to go put a dot at 467 and 280. So 450, 467, and 250, 280. Now, this one is going to be a solid line. Connecting those 2 intercepts and shading greater than. Okay, next, we're going to go do the other one from 400 to 400. That one's going to be a dashed line. And then that one is going to be shading less than. Now notice where the pink and the yellow touched, it made orange, and that's called our solution region. Make that nice and obvious that that's the region that is our solution. Use technology to graph the inequalities, sketch the solution region, include labels and scales for axes. If I were to ask you what is a point or a possible combination that works, you could say, for example, 100 to 50, which would be right here in the solution region. Okay. Oh, identify a solution to the system. And what that means is 100 lawn tickets and 250 seat tickets were sold. On this next scavenger hunt, if your teacher did this in class, the little solution is right down here to each one. Try pausing it and graphing them on your own and then checking the solutions. If you're ready for more, feel free to go on to this section and highlight your lesson summary, read through it. It's great right before the test to read through those lesson summaries.